Okay, can you hear me? Yeah, okay. So I guess we can get started. Welcome to lecture 4. Yesterday, we discussed a little bit about the definition of the transverse momentum dependent parton distribution functions and the fragmentation functions, connecting them to the objects that you can probe experimentally, namely the structure functions. We also understood what is the crucial role of the symmetries of QCD in the classification of these distributions. And in particular, we understood that there are two categories of distributions. There are the time reversal even, these TMD distribution functions, and the time reversal odd distribution functions. And a similar classification holds for the fragmentation functions, of course. The properties of the time reversal odd, the quark time reversal odd distribution functions, is to change sign between processes like semi-inclusive DIS and Rayleigh, or processes which are sensitive to a future pointing and a past pointing Wilson line. So this does not happen at all in the collinear case. So it's a property of the TMD sector. It's a striking prediction of the symmetries of QCD. It's a very important prediction that we should try to confirm or falsify experimentally, because it's connected to such a profound aspect of the theory, which are the underlying symmetries. Okay, today we are going to focus on something slightly different, which is factorization, the renormalization of these distributions of the evolution equations and the matching properties. So this is something slightly different compared to what we discussed yesterday, but it's connected. It's the first step towards establishing phenomenology. So it's what you need to do, factorization, these kind of things are what you need to do in order to extract TMD distributions from experimental data. So let's start with the first one, TMD factorization. So TMD factorization is the baseline for doing phenomenology because it's a theorem, or it's a set of theorems that allows one to connect an observable, like the cross-section differential with the transverse, with respect to a certain transverse momentum QT, for a process like the Rayleigh. So you have PP with an intermediate gamma or Z, and you have two leptons in the final state, lepton and anti-lepton. Shall we, let me see if I can, oh, okay, it's gone. Good. So the theorem tells you that you can connect the observable to transverse momentum distributions. These transverse momentum distributions are physical in the sense that they have been renormalized. They don't have any kinds of divergence anymore. So now you see that, so these are two transverse momentum dependent PDFs, the unpolarized one. The first one is related to the quark which is probed inside of the first proton. The second one is related to the other quark probed inside of the other proton. And what's the difference compared to what we saw until now? What do you see in these distributions? So they depend on X, they depend on KT. This is what we saw yesterday. And then what do you see there? Yeah, there are other two scales. Here they are set equal to Q and Q square, where Q is the invariant mass of the exchanged virtual particle. Okay, so, but in principle, they are two different scales. So there are two different scales because there are two kinds of divergences that you can renormalize. We're going to see that later. So, but remember that the physical TMDs are renormalized and they obey evolution equations with respect to these variables. It's like the collinear PDFs, but the collinear PDFs, they only have one renormalization scale. And the evolution equations for that scaling, the collinear case, is dictated by the Diglap equation. Okay, so in a nutshell, this is the result of a factorization theorem. So you have H that describes the hard interaction between the quark and anti-quark and the photon or the Z, whatever happens here. Then you have the initial state description, which is given to you by the two F1 distributions. You have this delta function here that again tells you that the transverse momentum of the quark, KT, in the first hadron, and the transverse momentum of the quark, KT, in the second hadron, they add up and they build the observed transverse momentum. And then you have corrections here, corrections to the factorization theorem, and we're going to focus on them later. Okay, so the meaning, the physical meaning is the following. for factorization to hold, the expression on the right and the expression on the left, they have to have the same infrared physics. So the infrared poles in the right and in the left has to be the same. Okay, for factorization to hold, the TMDs should describe and encode the non-perturbative physics that you have in your observable. The observed transverse momentum, QT, which is, for example, the transverse momentum of the photon or the lepton pair, is accounted for by the transverse momentum of the two quarks. But this transverse momentum of the quarks is not only the intrinsic one. So it's not only the transverse momentum that the quark has, let's say, when it just comes out of the proton. It has also radiative components. You see, the quark can acquire transverse momentum by kicking out gluons. So these radiative components is what you can calculate through the evolution equations. And the renormalization or the evolution equations, they tell us how to separate the intrinsic component, so what's in the wave function, from what is radiative. Okay, so when you put these kind of formulas at work, you see something like that. So these are experimental data from the CDF experiment at Fermilab for a Z boson production, differential with respect to the transverse momentum of the Z. You see that with such a factorized expression for the cross-section, you can actually describe the experimental data pretty well. So the dots here are the experimental points. The boxes are related to the theory calculation with the theory uncertainties, which are mainly coming from the collinear PDFs. Okay. So it's essential to have an approach, a theory approach that has predictive power. So an approach that lets you, which is predictive in the regime where perturbative QCD holds true. So it would be very difficult to achieve such a description with a non-perturbative model of the cross-section. You really need to have something that tells you how your TMDs evolve with the two evolution scales. You really need to implement the evolution equations in the TMDs, which are what make the formalism predictive. And those evolution equations, they come directly from the way you factorize this expression, this cross-section. So the two things are really connected to each other. Okay, so where does TMD factorization hold? There are three standard processes that involve the quark TMD PDFs or fragmentation function. The first one is Drellian. So if you have a charge current or neutral current, Drellian. So proton-proton scattering to lepton, anti-lepton, or lepton-neutrino. Semi-inclusive DIS, we discussed extensively about it. And also two hadron inclusive E plus E minus annihilation. So if you have E plus E minus annihilating and producing two hadrons, one hadron in one hemisphere and one hadron in the other hemisphere. There are factorization theorems, TMD factorization theorems also for gluon TMDs. So there are some observables like Higgs production in hadronic collisions or quark-anion production, pseudo-scalar quark-anion production, for example, eta B or C in hadronic collisions. For those, especially for the quark-anion case, it's still an open, it's still, the factorization for this kind of processes is not completely well established, I would say. It depends, the answer depends who you ask. Okay, so, but for sure, there is a lot of effort going on in this direction from the point of view of effective field theories, like in the SCAD community. Then there are also other processes which are, let's say, less mainstream, but they are becoming more and more interesting, especially for the theory community, but also for the experimental community, and they involve jets. Okay, jets have been studied since ages in the field of collinear physics, so it's not that we are inventing jet physics. But jets in the context of TMD measurements are something which has become popular in the last 5 years, I would say. Okay, so you can have semi-inclusive DIS with a jet in the final state rather than a single hadron, or you can have, or you can measure also two jets. It's like having one hadron or two hadron in the final state. You are less inclusive, you just measure, you are more inclusive, sorry, you measure just a jet. Or you can use jets and probe single out specific hadrons inside of the jet. This lets you measure spin momentum correlations inside of the jet. And we're going to see something later on. Then you can also have processes where you have, for example, E plus E minus annihilation. And in the final state, you have a hadron in one hemisphere and a jet in the other hemisphere. So, and that lets you measure, for example, the transverse momentum of this hadron with respect to the thrust axis of in the other hemisphere. These are a little bit more complicated. You can factorize these kind of processes using TMD distributions, but you also need jet functions, okay, and other objects which go under the name of soft functions that describe the soft physics in the event. Okay, so global fits, so analysis of the world data in order to get information of the quark TMDs or the gluon TMDs are available only for quarks, because for the other processes there are not enough data yet, or there are really no data at all to perform meaningful phenomenological analysis. So all the efforts related to global fits are confined into this top left box here. So they involve quark, TMD, PDFs, and fragmentation function, and the processes you study are Drellian, neutral current or charged current, and semi-inclusive DIS. For example, this process would be very, very interesting to include in the global fits, but unfortunately, we don't have the data yet. So I think the data exists since I was a graduate student, but I mean, the collaborations did not publish them, so that you cannot really use it for phenomenology. Okay, so let's see examples also on non-TMD factorizable processes. If you consider a process like proton-proton collision with two hadrons in the final state, this has problems. It cannot be factorized from the point of view of TMD factorization. You can describe it from the point of view of collinear factorization. There are certainly plenty of analysis involving this kind of processes in the collinear side. But in the TMD case, you cannot do it. The reason is that you cannot really disentangle the Wilson lines in the various correlators that you have here. So it's impossible in the TMD case to define objects, to have a factorization across sections with well-defined objects for the two initial states and the two final states. So there are actually in these papers counterexamples that tell you that factorization is violated in this case. I invite you to check them out. By the way, this endangers also processes where you have free hadrons. So if you have two protons in the initial state and one hadron in the final state. So there are no counterexamples to TMD factorization in this case, but there is also no proof. Okay, so it's kind of a tricky situation. We don't know really what happens. Are they useless? Are these processes useless? So if you ask me, I would say no, they are not useless because they could be very interesting in order to quantify the factorization breaking effects. So this analysis here, they tell us that TMD factorization does not work, but they don't tell you to which extent factorization is violated. They don't tell you factorization is violated by 10% or 1%. That's actually impossible to quantify without having the measurements first. So these other papers here, they try to provide tools in order to measure these factorization breaking effects. They actually try to give a TMD interpretation of these processes, proton-proton to two hadrons. And the idea would be to see what's the difference between the TMD factorized cross-section in this case and the experimental measurements. So this is a very interesting field of research if you want to stick your hands into it. Okay, let's go back to the previous formula. So our cross-section for Drellian differential with respect to transverse momentum. So keep in mind that factorization is always an approximation. It's not an exact result. There are always corrections to your factorized expression. So this means that you have to, in order to use the formula in a reliable way, you have to keep these corrections under control. Okay, if these corrections here, they grow too large, then you're not, the application of the factorization theorem is not legitimate anymore. So which kind of corrections do we have in the TMD case? The first one is a correction that becomes relevant when the transverse momentum is comparable to Q, and Q is the hard scale of the process. In this case, could be, for example, the virtual mass of the photon, the mass of the virtual photon, or the mass of the Z. Okay, so these are the corrections that become important at large transverse momentum, whereas the TMD region is what we identify with as QT being much smaller than Q, so the low transverse momentum region. TMD, PTS, and fragmentation functions are extracted from data only in this TMD region, so only when the transverse momentum is small compared to the hard scale of the process. So if your data sits in this region, so if your data have a QT which is comparable to Q, then you have to be careful. We're going to see later what is possible to do. And then you also have these kind of corrections where lambda is lambda QCD. So these corrections become important when the hard scale is very low and it's comparable to lambda QCD. So we'll say when Q is of the order of 1 GeV, then these corrections are also becoming a dangerous thing for your analysis. Okay, so the first one is related to the large QT region, as I said. So in a sense, if you want to keep this under control, you have to learn how to match your calculation from the low QT region to the high QT region. And this is the so-called matching, you need the so-called matching prescriptions, okay, to transition from the QT region to the large QT region. And okay, here there is quite a lot of work going on. For the other correction instead, these are related to higher twists in general. They could be the higher twist distributions that we discussed yesterday. They could be multi-parton correlations. They could be other things as well. So this is more difficult to keep under control. It's more difficult to address, I would say. Yes.
So I was curious to know if one wanted to prove factorization for some process, how would one go about doing that? Like, what would be the?
You have to make an analysis of the Feynman diagrams that are involved in the process, and you separate the different regions, say the collinear region, the hard region, and the soft regions in these diagrams, and you try to organize these contributions, separating the divergences in each of them. It's something which is explained very well in John Collins' book, for example. It's something that I was not planning to touch in these lectures, really the way you do it, because it's very advanced. But maybe later on we can talk about it if you want. It's a very interesting question. It's a very active field of research, so it's very relevant. Okay. So going back to the approximations. So these are the approximations that you see directly when you write down the cross sections. But there are also other kinds of approximations which are kinematical approximations. So you remember when we discussed semi-inclusive DIS, we were working mainly with the and also inclusive DIS. We were working with the X-Bjorkin variable, which is the ratio between Q square and the scalar product of 2p.q. Okay, this quantifies the collinear motion of the quark or the gluon with respect to the parent hadron. The factorization theorem actually is worked out in terms of another variable, which is the Nachtman X. And this Nachtman X is connected to the X-Bjorkin variable up to some corrections which are target mass corrections, because they are ratio of m over q, actually m squared divided by q squared, where m is the mass of your target. Okay, so if q is relatively large compared to m, so if q, say if you're using a proton, if q is relatively large compared to 1, then you can neglect them, okay? But if not, you have to be careful. So these are examples of kinematical approximations that sit inside these objects here, the X. So they are not like explicit corrections to the factorization approximations, but inside of the factorization approximations, you have this kind of kinematic corrections. The same holds true for the fragmentation variable Z. you have corrections proportional to the hadron mass. So this is a target mass corrections. This is a correction which is a function of the mass of the produced hadron. But on top of these, there are also inside of this formula corrections that depend on the ratio of qt square over q square. So they are hidden everywhere, this kind of kinematic corrections, and you have to be very careful in implementing the kinematics in your analysis. So this paper here actually is kind of a guide on how to use all these kind of approximations. And if you're interested in this topic, I really suggest you to look at it. Okay, so this is, for example, based on the paper here, an analysis which is performed at the for the kinematics of semi-inclusive DIS that tells you what's the relevance of this target mass correction on the definition of on setting up your kinematics in these different experiments. So you see the color here tells you how different are X-Nachtmann and X-Bjorkin. You see that, okay, in the kinematics of compass, it's relatively safe to identify X-Bjorkin and X-Nachtmann because the color is the bright green. If you go to experiments with where the data sits at a lower invariant mass, for example, let's look at JLab. There is a kinematic slice here where the corrections between the difference between X-Nachtmann and X-Bjorkin is 4%. 4%, I mean, what do you think? Is 4% a big effect or not? Who says it's a big effect? Hands up. Okay. I guess the other ones say it's not a big effect. So it can be a big effect. It depends on what you want to measure and calculate and what is the precision of the observable you want to describe. If you're after an effect which is order 1%, like, I don't know, some kind of asymmetry or an higher twist effect, or even very, very precise data about the unpolarized cross-section, then 4% is a relevant effect that you have to take into account. So the answer, yes, it can be relevant. It depends on what you want to calculate and what your experimental colleagues have measured. So just keep in mind that there are approximations everywhere, and it's actually the job of a phenomenologist to understand how to use approximations. Okay, let's look at the TMD evolution part. The evolution equations come from the normalization of the distributions. The practical effect is that we can use them to zoom in hadron structure. Okay, if you want to resolve the structure of your hadron at a higher scale, mathematically you do it by using the evolution equations. So evolution equations are more easily implemented for the Fourier transforms of the TMD distributions. So you take, I'm using now capital F for labeling a generic TMD distribution function. So you have a TMD distribution in momentum space, and you Fourier transform it to BT space. BT is the Fourier conjugated variable with respect to KT. So there are 4 kinds of equations that you have to take into account. So F evolves with respect to Xi with this anomalous dimension, D. In the literature is also called K, but everyone knows it as the Collins-Hopper kernel. Okay? So this anomalous dimension also evolves with respect to mu, and the gamma cusp is the anomalous dimension for its evolution. So the first one and the first and the third one are connected. Okay? Then you have the evolution of F with respect to mu, related to the UV divergences. And you see the anomalous dimension for this evolution also has its own evolution equation. So you have two equations for the TMDs and 2 equations for the anomalous dimensions of their evolution. So 4 in total. Let's try to look at the solution of these, at the combined solution of these 4 equations. So if you take your TMD PDF in BT space, so the solution of the evolution equations can be written in the following way. You have the function at 2 other scales that we call them mu0 and zeta0, which are the initial values for your scales. So mu0 is the initial value and mu is the final value for the evolution, and the same for the zeta variable. Then you have an evolution in mu, which is driven by gamma f, okay? And you have another evolution in zeta, which is driven by the Collins superkernel d. Okay, so it's pretty simple in the end. The difficult part is to, look at the expression of gamma f and d. Depending on the perturbative order at which you work, these expressions gamma f and d have different components, of course. They are perturbative series in alpha strong. So the good thing, the interesting thing, is that the anomalous dimensions are of course, calculable in perturbation theory. So you can work out perturbative calculations for those. The unfortunate thing is that for the evolution in zeta, you also have a non-perturbative component, something which is non-calculable in perturbation theory, and it shows up when Bt becomes large. Okay, so when Bt becomes large, and large is yet to be defined, you have a correction to the evolution equations here. Now let's look at the initial state, so the initial condition, f of x bt square mu 0 zeta 0. This distribution here can be expressed or refactorized in technical language on the basis of the collinear distributions, okay? So this expression here tells you that you can write your TMD PDF as a function of the collinear PDF times coefficients which are calculable in perturbation theory, okay? So these coefficients here are also related to, say, the perturbative splitting of a quark in a gluon, for example. They contain the D-glap splitting terms as well. So the type of collinear PDF that you have here depends on the type of TMD PDF that you're considering. If you have a leading twist TMD parton distribution function, then here you have the unpolarized, more or less you have, that's not an exact statement, but in the simplest cases of TMD distribution functions, you are matching your distributions on the leading twist collinear parton distribution functions. If you have a T-odd TMD PDF, here you will have higher twist collinear parton distribution functions, but I don't wanna dig into it. So what I want you to remember is that TMD PDFs are related to collinear PDFs in this scheme, okay? So also this expansion, this matching of the TMD PDFs on the collinear ones needs a correction, a non-perturbative corrections at large BT, okay? And in a sense, we have to trust the people who give us expressions for the collinear PDFs when we want to make a phenomenological analysis of TMDs. So this can be taken, for example, from a global fit of collinear PDFs, or if you want to do something more exotic, you need a model calculation for the collinear function here. So the take-home message is that when you describe a TMD distribution function from the point of view of the evolution equations, you have objects that you can calculate in perturbation theory, the two anomalous dimensions, gamma f and d, and these expansion coefficients c, but you have non-perturbative corrections. These non-perturbative corrections are related to the intrinsic transverse momentum distributions. So are really related to, say, the transverse motion that the quark has from the point of view of the non-perturbative wave function. Okay, so this is what you go after when you try to extract the TMD distributions from the experimental data. Okay, so you combine perturbation theory to calculate whatever you can calculate, and these are the objects that you want to extract from the data. Okay, so I think what we have to keep in mind at this point is the following. When BT, the variable which is conjugated to KT, to the transverse momentum, is small, the TMD PDF can be calculated in perturbation theory, and you're focusing mainly on the radiative contributions. When BT is large, you're sensitive to these non-perturbative corrections. Okay, these are relevant only, they have to be relevant only when BT is large. And large, yeah, it has to be quantified what large means, but typically large is 1 inverse GV. Okay, this is something that we also see from the phenomenological analysis. Okay, so small bt we can calculate. Large bt, it's the non-perturbative part. So at this point, the question is, how can I know if my TMD PDF or TMD fragmentation function is dominated by non-perturbative components or components that I can calculate in perturbation theory? Do you have a, I mean, okay, here yeah, okay. Or in other words, in which kinematic region is your formalism predictive? So in which kind of regions perturbation theory dominates? If perturbation theory dominates, it means that you have everything under control in your calculation. So you can predict an observable that you don't know in a reliable way. Okay. Whereas if your calculation is dominated by non-perturbative effects and you don't know these non-perturbative effects, then it's very difficult, impossible to make a reliable prediction for an observable. So, any of you has an idea? So what would you do? What would you do to understand if your TMD is dominated by non-perturbative contributions or radiative contributions? So I can give you a hint. In BT space, usually in BT space, so if this is BT, okay, the distributions, they can look like this. So if the distribution in BT space is the following, what would you think? Twice? The data, but before having data. Okay. Yeah, so what? So no, so this is BT space. So we said that small BT can be calculated in perturbation theory. Large BT is non-perturbative, so we don't know. So say, for example, say that this is 1 inverse GV. So this is inverse GV, and this is 1. Okay. So if the situation is the following, remember that the physical TMD, so the TMD momentum space is related to the integral of this function here in BT space. If the TMD, since the TMD in KT space is related to the integral of this one, you have to see where the peak of the distribution is or where the bulk of the distribution is. If it is in the small BT region or in the large BT region. Namely, if the bulk of the distribution is before 1 GeV, it means that this area here will contribute most to the TMD in KT space, and that distribution will be dominated by perturbative contributions. So if the function is like this, the integral here, the area under the curve here is completely in the small BT region. In this case, the function in KT space will be completely perturbative. If the situation is like this, for example, okay, only a fraction of the area under the curve lies at small BT, whereas the majority of the contribution comes from the large BT region. So in this case, the TMD will be dominated by non-perturbative effects. So the idea is to try to understand where the peak of the distribution is as a function of the kinematics. Okay, so to do that, one can use the saddle point approximation. So the saddle point approximation tells you that if you have an integral of this type, an integral of the exponential of a certain function f of x, and this function has to obey certain condition. It cannot be a rapidly oscillating function. It has to be like a relatively smooth function. Then you can evaluate the whole integral by evaluating the integrand at a specific point that we call x0. And that point is called the saddle point. And it corresponds to the stationary point of the function f. Okay, so you can use this approximation to calculate where you can use this approximation for the TMD PDFs. And in this case, we try to analyze where the position of the function in BT space lies. So we try to calculate where the saddle point in BT space is. So this BTSP means BT saddle point, in order to understand how BT saddle point changes as a function of the kinematics. So the idea is that we want to see how the peak of this distribution shifts in BT space as a function of the kinematics of your experiment. Let's try to do it at the board. Okay. So I'm gonna switch to the board for a few minutes. Okay. So let's write down, first of all, the relation between the distribution in momentum space and in BT space. So that's the Fourier transform that you can rewrite for the unpolarized TMD PDF. You can rewrite it with in this way using the J0 Bessel function. Okay. So in order to apply the saddle point approximation, we said that the integrand cannot be rapidly oscillating. So the J0 function is a very rapidly oscillating function. So what we do is the following. We try to do this analysis of the saddle point for KT equals to 0. For KT equals to 0, yes? Oh, sorry, yeah. Thank you. Okay. So we use KT equals 0, Q1 Q square, okay? And in this case, the Bessel function becomes equal to 1. So this is the integral between 0 and plus infinity. Okay, you have BT f of a x BT square Q square. Okay, so in order to be able to use the saddle point approximation, I want to have an integral between minus and plus infinity, not between 0 and plus infinity. So one possibility is to change the integration variable in this way. Okay, you can perform the calculation by yourself also. You have an integral, we switch to the log of BT square. This becomes 4 pi. And here we have an extra power of BT, so this becomes BT square. And you still have f of x BT square. Let me now avoid writing Q and Q square. Let's drop the Q and Q square dependence for now. Okay, so now I'm integrating between minus and plus infinity, but I also want an exponential function here. So what I simply do is to rewrite this as the exponential of the log of BT square times f of x BT square. Okay, so now we are in the situation where we have an integral between minus and plus infinity, the exponential of a function, and the function in the exponential is not rapidly oscillating. Okay, so we can safely apply the saddle point approximation in this case, which is also called the Laplace approximation. All right, so the saddle point is a stationary point for the argument of the exponential. So we have to look for the stationary point of this function with respect to the log of BT square. So you can show that instead of calculating the derivative with respect to log of BT square, you can also calculate the derivative with respect to BT directly. And what you get is the following. So you have to find the value of BT that I call BT saddle point, such that the derivative with respect to BT of the log of BT square times your TMD in BT space, evaluated at BT equal BT saddle point, is equal to 0. Okay? So this equation here tells you the point that basically dominates the integrand or the integral itself in BT space. So if we understand how this point here moves as a function of x and q square, we know if in that kinematic regions the TMD function is perturbative or not. So we're going to see exactly how it works. So okay, so if you remember the function f in BT space, the perturbative structure, so the solution of the evolution equation depends on three objects that you can calculate in perturbation theory. Gamma f, the Collins upper kernel, and the matching coefficient C. So in principle, solving this equation is pretty complicated if you work at a high order in perturbation theory. But you can also work at the lowest order in perturbation theory, and in that case, you get an analytical solution for this. So if you work at the leading log approximation, the so-called leading log approximation, you can show that this equation here, so only the leading order term in the gamma cusp anomalous dimension survives, and everything else can be neglected. And you can show, I'm not going to go through the details, but if you are interested, we can work it out together later on. This equation here boils down to the following one. 1/2 the log of q square divided by mu b star squared gamma 0, which is related to the cusp anomalous dimension, is the first non-vanishing term. Then you have the coupling constant alpha strong evaluated at this scale mu b star that I'm going to define in a few seconds, divided by 4 pi. And then at the right-hand side, you have 1 minus a function capital X, which is a function of the partonic X, comma, mu b star. Okay, so what are the ingredients here? So this capital X function is nothing else than the derivative with respect to the log of mu square of the unpolarized PDF. Okay. And let me write it here. The scale mu b star is a constant divided by the saddle point BT. So the saddle point equation, the generic one, let me repeat this. If I work at the leading log approximation, so the lowest approximation that you can do in perturbation theory, becomes this one, and which has an analytic solution. And we're going to see what the solution is. So you see that the saddle point will depend, in a sense, on the behavior of the collinear PDF. And why do we have a collinear PDF in the game? Do you remember? Yeah, so we are going to get a KT equal to 0, but the collinear PDF emerges from the fact that the TMD was matched on the collinear parton distribution functions. So in the solution of the equations, we saw that the TMD PDF can be written as a function of the collinear PDF as well. Okay, so let me go to the other side. Okay, so this is actually pretty useful. Let's try to calculate to see what the alpha strong, the coupling constant, is as a function of mu. So you can use the RG equation for alpha strong. So the derivative of alpha strong with respect to mu square is given by the beta function. Okay, and this is a power expansion in alpha strong. And since we are interested in working at the lowest order, we keep only the B0 term. Okay, so these are suppressed as powers of alpha strong, and we don't consider it. So if you neglect this one, this actually has an analytic solution. You can separate the variables and you can find an analytic solution. And the solution is the following. You have alpha strong as a function of mu square. This is equal to B0 times the log of mu square divided by lambda QCD square to power -1. Okay. So now I stick this expression for alpha strong in the saddle point equation over there. And this is what we get. We get 1/8 pi, the log of q squared divided by mu b star squared, gamma 0, and then I have alpha strong, right? So I have 1/b0, the log, the inverse log of mu b star squared divided by lambda squared equal to 1 minus the x function, the capital X function here. So I did nothing but rewriting alpha strong actually. So I included here the expression of alpha strong as a function as a function of the renormalization scale. Okay, now we want to try to isolate BT saddle point. So BT saddle point sits inside of these variables here. So I remind you that mu B star is actually C divided BT saddle point. Okay, so what can we do? In order to make our life a little simpler, we start by removing this function here. So we approximate the equation by saying, okay, I want to neglect the x-dependent part. So capital X is the only x-dependent part. So the x-dependence in this equation comes only from the derivative of the collinear PDF. And we say, okay, let's forget about it first and see what happens. If I neglect that, my equation, so if I work in the assumption capital X equal to 0, the equation becomes 1/8 pi gamma 0 divided by B0. Then I have a ratio of two logs. The log of Q square BT saddle point squared divided by C squared, and the log of C square divided by BT saddle point squared. This is lambda squared, yes, equal to 1. Okay, I'm just combining the logs here. Now, okay, let me save some chalk and algebra, and let's go to the final steps. So what you can get from here, if you isolate BT saddle point as a function of everything else, is the following. So the saddle point of your TMD PDF is equal to the ratio between this constant and lambda. Then you have another ratio of Q divided by lambda. where lambda is lambda QCD. Okay. And the exponent here contains gamma 0 and B0, basically. Gamma 0 plus 8 pi B0. Okay, great. So gamma 0 and B0 are numbers. Lambda QCD is a number, pretty well known. C is a constant, we don't care too much about it. What is the only kinematic dependence of the saddle point? Q, right? So in this case, BT depends only on Q. Okay. So let's try to see what happens. If Q is large, what happens to BT, saddle point? I mean, one has to know the numbers for these constants here, but what happens is that when you increase Q, BT saddle points become small. When Q is low, BT saddle points is large. So this tells you that the TMD PDF becomes non-perturbative when Q is small. Okay, this is the equation that represents from the mathematical point of view the common knowledge that TMDs are non-perturbative at low Q and perturbatively dominated by radiative contributions at high Q. Okay, so this represents from the mathematical point of view what we know also from the experiments. And by the way, this is exactly the results that was contained in the early papers by Collins, Soper, and Sterman in 1985, and even earlier by Parisi and Petronzio. In 1979, yes. So in these two early papers, these famous people here studied the cross-sections as a function of the observed transverse momentum for Drellian or Z-boson production. And they argued that for those cross-sections, the non-perturbative contributions dominated small q, whereas they vanish at large q. And this is exactly the equation that they had in the paper, okay, at least in the CSS case. You can derive this equation using the saddle point approximation for the TMD. So this is a slightly different derivation, but you get the same result. So BT saddle point has a Q dependence, but we neglected the capital X. Okay, so in principle, if you consider the X as well, you can have also an X dependence of your saddle point. So this becomes, if you take into account the capital X contribution, okay, this result is modified, is actually modified in the following simple way, analytically. Here you get 1 minus capital X of X mu B star. Okay. So now you see that your saddle point is X dependent, and the derivative of the collinear PDF drives this X dependence. So, okay, now it's difficult to get an intuitive understanding of the X dependence because the dependence is more complicated. It's in the ratio, in the denominator of the power, and it's the derivative of the PDF. So I'm gonna show you what the result is on the screen. Can I switch back to the, oh, it was automatic? Okay. So can we go back to the slides, please? Let me see. Maybe I have to share the screen. Yes. All right. So, okay. So this is the XQ square plane. So no, this is the X saddle point plane. So you have BT saddle point, this quantity here, as a function of X, the collinear momentum fraction, and Q. And in particular, we are working at the value of Q, which is given by the Z-boson mass, so 91 GeV. Okay, so pretty high Q. The orange line is X independent, and it corresponds to the solution of the saddle point equation without the x function. So no x dependence. The saddle point was a number. So the saddle point was around 1 GeV, okay, at the boundary between perturbative and non-perturbative. Okay, I'm almost done. The purple line is the solution, analytic solution for the saddle point with x and q dependence. So now we fix q equal to 91, and we see what the x dependence here, and it's driven by the derivative of the PDF. You see that if you go to small x, the saddle point lies close to the perturbative region, in the transition region. Let's say it's perturbative, basically. So if you go to smaller and smaller x, the saddle point decreases. So it means that at small x and high q, the TMD PDF is dominated by perturbative contributions. Whereas if you increase x, you go towards 0.1, for example, you see that you transition to the non-perturbative region. So even if you're sitting at a very high q, changing x has an effect on whether the TMD PDF is perturbative or not. The dots here represent the numeric solution of the saddle point equation there on the board if you were doing the calculation at 2 loops, okay? As I said before, if you're considering higher orders here, you cannot get an analytic solution, but you do it numerically. And you see that the trend more or less is the same. So you have different colors for the dots because the different colors correspond to having different non-perturbative parameterizations. And you see that at large x, the value of the saddle point for different non-perturbative content is different. So it means that the non-perturbative corrections become relevant. It's exactly what we're saying. So okay, I had another topic, but maybe we can discuss it after lunch. Asmita, what do you think? Asmita, what do you think? We can continue after lunch, or should I take 10 minutes more? What do you think? I have another lecture. No, sorry. After lunch. I don't know, 10 minutes. Well, I mean, I can also do it later. That's no problem. I think it's a good point to stop also. Okay, let's stop. Okay, do you have questions? So try to digest this calculation and repeat it by yourself. I think it's quite a useful calculation to get an intuitive picture of, let's say, the relevance of the different contributions in the TMD PDF. It tells you also in which kinematic regions experimentally you should expect your experimental data to be more informative about hadron structure or just the perturbative structure of the theory. Okay.
Okay, let us thank Andrea for a very nice talk.